Okay, let's talk a little bit about change in free energy, delta G, and how that affects the spontaneity of the reaction or physical process. Willard J. Gibbs determined that there was a relationship between the enthalpy and entropy that best described the maximum useful energy and consequently the spontaneity of the reaction, as long as we had constant temperature and pressure. Okay, let's talk about free energy change, the delta G, and the spontaneity. Turns out Willard Gibbs determined that the relationship between the enthalpy and the entropy best described the maximum useful energy for a chemical reaction or a physical process, which in turn will determine whether or not it's spontaneous. And that work would be performed at constant temperature and pressure. The relationship is the delta G, or the Gibbs free energy. And we can express that as delta G equals delta H minus T delta S at constant temperature and pressure, where temperature has to be in Kelvin. We can still calculate the Gibbs energy using the values in the table, and we'll work through that as well. So the change in the Gibbs energy is a reliable indicator of the spontaneity of the process. It does not tell us how quickly the reaction occurs. That's the job for kinetics. So the sign convention is that a positive delta G is non-spontaneous. A delta G equal to 0 is a system at equilibrium, and a delta G that's negative is a spontaneous reaction. Changes in the free energy have the same type of relationship we've discussed for enthalpy in the first semester and entropy in the video just previous to this one, if measured under standard conditions. So if everything's standard, you can get it out of the table. Delta G standard, assuming we're at room temperature 298 Kelvin, is going to be the sum of the delta G's of the products times their coefficients minus the sum of the delta G's of the reactants times their coefficients. And so, again, here's our friend the propane reaction, and we're going to work through how to get the delta G for that particular reaction, but from the table, not using the delta G equals delta H minus T delta S. So we'll go to the paper, and again, we're going to use Appendix C. And I won't go through this quite as much detail as I did in the previous video, but we're going to be focusing on this column. But notice delta G's for elements are 0, where they weren't for the entropy, and they are for the delta H and for the delta G, so for free elements. So in our case, the oxygen is going to be 0 because it's a free element. I'll have to look up values for everything else. So let's work through that. The delta G standard for this particular reaction is going to be equal to our products. So it's going to be 3 moles times the delta G standard of formation for CO2 plus 4 moles times the delta G standard of formation for the water. Those are my products. From that, we're going to subtract the reactants. So we're going to have essentially 1 mole delta G standard of formation for the propane plus 5 moles delta G standard of formation for the O2. Now what we just said is that this term is 0 if you look it up. So really this whole term goes away and is 0 because the Gibbs energy of the oxygen is 0 for a free element. We'll work on calculating the rest. And so we'll have 3 times, then we're going to look it up for CO2. The Gibbs energy is going to be a negative 394.4 kilojoules. And that'd be kilojoules per mole, but I'm canceling with the mole there, plus 4 times, and then we're going to look it up for water. In the gas phase, so make sure you pay attention to phase again. Water in the gas phase is a negative 228.57 kilojoules. That's my product side. Then I'm going to subtract the Gibbs energy for the propane. So for propane, the Gibbs energy is a negative 23.47 kilojoules. So then we're going to run that through our calculator. We got 23.47. Notice it's minus a minus, so it's going to end up being a plus. So our delta G for our reaction is a negative 245. Let me see, we're going to go to the tens place, 0.6 kilojoules for that particular reaction as a whole. So looking at the table, we can actually say some things about spontaneity of the reactions based on the sign of the delta H, the delta S, and the delta G. So if the delta H ends up being negative and the delta S ends up being positive, then the delta G equals 0, because we're looking at the delta G equals delta H minus T delta S. And so you've got to plug things into that. And the bottom case, if delta H is positive and delta S is negative, then the delta G is positive, and it's non-spontaneous. Those are just always, regardless of temperature. The two in the middle are temperature dependent because they offset. If delta H is negative and delta S is negative, we got conflicting things because the enthalpy is favorable, but the entropy isn't. So it'll be spontaneous at low temperatures. If the delta H is positive, not favorable condition, but the delta S is positive, favorable condition, again, it's temperature dependent, and it'll be spontaneous at high temperatures where the entropy will dominate. So if we look at that on paper, we've got delta G equals delta H minus T delta S. It makes sense if this is negative, but that is positive, where temperature is always positive, right? So subtracting a positive will be negative, so that means delta G will end up being negative and will be spontaneous. Now, if delta H is positive and delta S is positive, I've got a mixed bag. It will only be negative if this T is big enough to allow the entropy to dominate. So this is spontaneous at high temperature. Now, and so this depends. And so if delta H is negative and delta S is negative, now this is favorable, but that's not. So again, it depends. So I want this to be low because I don't want entropy to dominate because it's not favorable. So this will be spontaneous at low temperature, or this is just spontaneous at any temperature. Now, if the delta H is positive and the delta S is negative, neither of those conditions, and so that's going to be positive room temperature, so it is non-spontaneous at all temperatures, and that's how that would work. And that works because the temperature's in Kelvin and therefore always positive. So let's look at a graphical relationship of that where the delta H and the delta S are related. It's non-spontaneous in the blue section and spontaneous in that pink section. So if delta H is positive, it tends to be non-spontaneous. So in the case where the delta H is positive and S is negative, that was that fourth case where they're both not favorable, it's going to be non-spontaneous at all temperatures. But if the entropy is positive, if I get the temperature high enough, it will cross into non-spontaneous territory eventually. If the H is negative, which means it's favorable, if the S is also positive, meaning in two favorable conditions, it'll always be spontaneous no matter the conditions. However, if the S is negative, non-favorable condition, you'll eventually reach a high enough temperature to where it is non-spontaneous. Now, if you say, for example, dissolve ammonium nitrate into water, the temperature will decrease even though the ammonium nitrate goes in. It's spontaneous, but endothermic, that you get a higher disorder dissolving the solid into the liquid. And I'll try to link in a video that shows this. We dissolve calcium carbonate into HCl. It's spontaneous due to a entropy-driven process. That is, it is much higher entropy because I end up forming a gas. So those are a couple of examples. So let's estimate the normal boiling point for water based on what we know for water. So our basic reaction is going to be H2O in the liquid phase going to form H2O in the gas phase. And I want to estimate what that boiling point is. Now, at the boiling point, that is at a phase change, this is an equilibrium. So we want to find at what temperature those two are at equilibrium. That is the boiling point. We know what it should be, right? It should be about 100 degrees Celsius or about 373 Kelvin. Now, you won't get precisely the right number, but it'll give you a good ballpark if you use our thermodynamic data. So what we're going to have to do is calculate a delta H and a delta S for our water data to actually estimate the boiling point. So I'm going to need figures from Appendix C again for water in the liquid and in the gas phase. So we'll just look those up, but we're not going to use delta G. We're going to use delta H and delta S. So we got water in the liquid and in the gas phase. So our delta H standard for the reaction is going to be the standard heat of formation for the gas phase, since that's the product, minus the delta heat of formation for the water in the liquid phase. And so if we look that up, water in the gas phase is a negative 241.82 kilojoules per mole, minus the liquid phase. So you're going to go minus a minus 285.83 kilojoules per mole. So that would be the delta H. The delta S standard for the reaction is going to be the entropy standard formation for the water in the gas phase, entropy standard, or not formation, entropy standard of the liquid phase. We look those up. So we're talking entropy now. So for the gas phase, it's 188.83 joules per Kelvin mole minus, in the liquid phase, 69.91 joules per Kelvin mole. Then we can run that through our calculator. So we're going to say negative 241.82 plus 285.83. And so boiling is going to be endothermic, so it's a positive 44.01 kilojoules per mole of water that boils. And you'd expect boiling to be endothermic, but I should get an increase in the entropy. And so we get, again, positive 118.92 joules per Kelvin mole. And so we've got a case with a positive delta H and a positive delta S. So this will only be spontaneous or even equilibrium if the temperature gets high enough. I can't boil something unless the temperature gets high enough. So that makes perfect sense. But I've got mix and match units, so I'm going to go to 0.11892 kilojoules per Kelvin mole. I've got to make the units match before I can work my delta G equals delta H minus T delta S. And these are all standard. If these values are standard that you plug in, then the delta G is also standard. If they're under non-standard conditions, then you would eliminate this little zero up there and not have it in standard conditions. So delta G standard is 44.01 kilojoules per mole minus our temperature times 0.11892 kilojoules per Kelvin mole. But what we know is since we're at equilibrium, delta G is equal to 0. And so then we're going to do a little algebra and say so we're going to say T times 0.11892 kilojoules per Kelvin mole equals 44.01 kilojoules per mole. So then the temperature is going to be 44.01 kilojoules per mole divided by 0.11892 kilojoules per Kelvin mole. So the moles should cancel, the kilojoules should cancel. I got 1 over Kelvin in the denominator, which will become Kelvin in the numerator. Run that through our calculator. And we're going to get about 370 Kelvin. Hey, for just using table values that's actually pretty close estimation of the boiling point. So that's one way we can use this. We'll look at some other applications in some upcoming videos.